Hey everyone, welcome. Today we're diving into a super fundamental concept from Physical Science Unit 2, Principles of Energy and Transformation. In this explainer, we're going to put on our scientific investigator hats and tackle a really interesting question. Where exactly does energy go when systems change? I know, it sounds pretty simple on the surface, right? But honestly, tracing how energy moves, transfers, and conserves itself, it's literally one of the most fascinating processes in the entire physical world. So let's just jump right in. Let's kick things off by confronting a totally classic misconception. Are heat and temperature the exact same thing? And does a bigger object automatically have more heat energy just because it's, well, bigger? If you went out and asked people on the street, honestly, most of them would probably say yes to both. We use the words heat and temperature interchangeably in everyday life all the time. But in physical science, words have very specific, measurable meanings. And today, we're going to look at some hard evidence to bust this myth wide open. So here's our quick roadmap for this explainer. First, the heat versus temperature myth. Second, average versus total energy. Third, analyzing some actual lab data evidence. Fourth, reaching thermal equilibrium. And finally, the final prediction challenge.
All right, Section 1, the heat versus temperature myth. Let's bust this thing.
Okay, let's break down these two concepts side by side. First up, we've got temperature. Scientifically speaking, temperature is simply a measurement of the average kinetic energy of the particles in a substance. The key word here is average, like how fast are those tiny microscopic particles vibrating or zipping around on average. Then on the flip side, we have thermal energy, which a lot of people just casually call heat energy. Now, this is the total kinetic energy of all the particles combined, not the average, the grand total. Think about it. If you have 1,000,000 particles, thermal energy is the sum of every single one of their individual energies added together. Grasping this distinction between average and total is absolutely crucial. It completely changes how we view the physical world around us. Moving on to Section 2, average versus total energy, why mass matters. Now, this comparison is going to completely flip your everyday intuition upside down. Picture a giant iceberg next to a tiny cup of boiling water. Let's think about the boiling water first. It obviously has a super high temperature, right? That means the average kinetic energy of its particles is extremely high. They are literally zipping around furiously. But it has a really low mass. There just aren't that many particles in one single cup. Now, picture that giant iceberg. It has a very low temperature. Its particles are pretty sluggish, meaning a super low average kinetic energy. However, that iceberg is massive. It contains trillions upon trillions of particles. Because thermal energy is the total energy of all those particles combined, that massive iceberg actually possesses way more total thermal energy than the tiny cup of boiling water. It's wild, but true. Mass totally matters when we're calculating the total. All right, Section 3, analyzing lab data evidence. Time for some energy transfer proof. So this data is going to help us see exactly where energy goes when systems change. We're considering a standard energy transfer lab setup here. Think about this setup. We've got time over a span of 5 minutes, object A's temperature, and object B's temperature. At minute 0, object A starts off nice and hot at 80 degrees Celsius, while object B starts cool at just 20 degrees. When we put them in direct contact, watch what the data does. It's basically a race to the middle. Minute by minute, object A's temperature drops and object B's rises. But here is the really cool part. Notice the conservation happening here. The energy didn't just vanish into thin air from object A, it transferred directly into object B. By minute 5, they've both converged at exactly 50 degrees Celsius. Object A lost the exact same amount of thermal energy that object B gained. The total energy in the whole system remained perfectly conserved. Which brings us to Section 4, reaching thermal equilibrium, finding that balance. So when the temperatures of object A and object B finally stopped changing at that 50-degree mark, they reached what scientists call thermal equilibrium. This is that exact sweet spot where the energy transferring from the hotter object to the cooler object finally results in a shared common final temperature. At this specific point, the net transfer of energy just stops. The average kinetic energies of the particles in both objects have perfectly balanced out. They're completely in harmony. Now, based on that lab evidence we just looked at, we can definitively trace energy transfer using 3 absolute rules. First up, energy always flows from hot to cold, from the higher average kinetic energy to the lower. It never, ever goes the reverse way. Second, thanks to the law of conservation, the energy lost by the hot object exactly equals the energy gained by the cold object. Nothing is destroyed, it's just relocated. And third, that whole transfer process continues until it hits thermal equilibrium, where the temperatures equalize and the net transfer officially stops. This right here is the definitive answer to our big essential question about where energy actually goes.
Let's wrap things up with Section 5, the final prediction challenge. Time to test your knowledge.
Okay, I've got a final transfer scenario for us to think about before we go. Imagine we have object X. It's boiling hot at 100 degrees Celsius, but it's pretty small. It has a mass of only 50 grams. Then we have object Y. It's sitting cool at 20 degrees Celsius, but it's much larger, packing a mass of 200 grams. That's 4 times the mass of object X. If we put these two objects in contact, well, we already know energy is going to flow from hot to cold, from X to Y. But based on what we just learned about mass and total thermal energy, with that whole iceberg and boiling water example, where do you think the final equilibrium temperature will actually settle? Is it going to be right smack in the middle at 60 degrees? Or will that massive 200-gram object pull the final temperature closer to its own starting point? I want you to take your brand new understanding of energy transfer and mass and predict the outcome of this scenario. Think it over and keep questioning how energy shapes the physical world around us.